Hello,
Recording in
everybody, and
progress.
welcome back to our conversation about freezing point depression. In our last video, we had a broad overview of what freezing point depression was, how it works on a molecular level, and I also introduced the equation that we utilize to quantify the degree of freezing point depression. And what I want to do now is I want to do a practice problem that allows us to get familiar with all these new terms we've seen in this equation. So let's take a look at this problem. So I have an example problem here. It says benzophenone has a freezing point of 49 degrees C. So this is a very volatile substance. And a 0.450 molal solution of urea in this solvent has a freezing point of 44.59 degrees C. Okay, let's just pause there. So benzophenone has a freezing point of 49 degrees C. So I'm going to start like identifying what information I know about one substance. So I have benzophenone. We know that this is a pure substance, right? I haven't talked about a solution yet. I've just said this substance has a freezing point of 49.00 degrees C. And then let's see here. What other information do we have about benzophenone? Let's see here. None that I can see. So let's maybe move on to our other component in solution. So continue reading. Benzophenone has a freezing point of 49 degrees C. A 0.450 molal solution of urea in this solvent. So we've identified benzophenone as the solvent here, right, in this solvent. So this is for sure our pure solvent, which means that our solution is a solution because we have added the solute of urea. So this is our solute. And we know a couple of things. We know the molality of urea is 0.450 molal. And we also know the freezing point of the urea in our solution. We know that that freezing point is, let's see here, let's identify it, 44.59 degrees C. Okay, and this is kind of stuff that's specific to our solute. And then some other information I was given. If this urea benzophenone solution has a freezing constant, okay, so then for the solution, I do know the freezing constant. Of 9.80 degrees C per molal. Now we get to kind of the meat of our question, our goal. What is the Van't Hoff factor of urea? So our goal. We want to find I, which is the Van't Hoff factor of urea. Now we can make some kind of educated guess here, right? Urea does not sound like an ionic compound, right? It does not sound like something I, like sodium chloride. It doesn't sound like something ate, like potassium sulfate. It doesn't sound like an acid, right? Like it doesn't sound like hydrochloric acid or perchloric acid. It sounds like it has just a name, like sucrose has a name, or glucose has a name, or fructose has a name, or ethylene glycol has a name. So our suspicion is that since this is probably a polar covalent solute, PCS, polar covalent solute, we expect for there to be little to no dissociation. So we predict that I should be close to 1. But let's see if that's true. Let's see if urea dissociates in benzophenone somewhat. All right. Since we are given information relating to freezing point, let's put our freezing point depression equation up on the board. So we have delta TF is equal to negative KFIN. And I'm going to rearrange this like right off the bat before I start introducing any numbers to get I by itself. So I'm going to rearrange this so that I have I isolated. So I'm going to divide both sides by negative KF and M. So I is equal to delta TF over negative KF M. And let's see if we can't figure out our delta TF, so our change in freezing point. So delta TF, this guy. So remember, this is our change in freezing point, meaning it's a comparison of our freezing point of our solution compared to that of our pure solvent. This should always be a negative change because freezing point depression implies we are always going to have a lower freezing point in our solution compared to our solvent, right? But let's confirm this is true numerically. So the freezing point of our solution was 44.59 degrees C minus our freezing point of our pure solvent, 49.00 degrees C. Okay, that is how we would find delta TF. Now we have to plug in our KF. So we were given the freezing constant for the solution. In the problem. So this is 9.80 degrees C per mole times that molality which we were given in the problem. So that is our 0.450 molal. Okay, let's chunk this out just a little bit. Like let's at least get our numerator and denominator straight just to ensure that our calculators aren't lying to us, because remember, we are not using graphing calculators in this class. We are using our scientific calculators. So we have to keep track of all of our math steps ourselves. So this becomes negative, drop my negative there, 4.41 degrees C over negative 9.80 times 0.450. This gives us negative 4.41. And let's check our units from this math we did in the denominator. So we are going to have molal over molal, leaving degrees C. And wow, what do you notice? Our prediction was right. This is equal to exactly 1. And we can again kind of check our sanity that I should equal 1 for urea. So urea is a polar covalent compound. In other words, it is not an electrolyte. So we would expect to see no dissociation. I could spell that word. There we go. Upon dissolution. So its Van Hoff factor should be 1. So yay. Our kind of rational sense about our prediction does match indeed what we find here. So this is how we can apply the freezing point depression equation. I can ask you for things that are a little bit more interesting, like we've seen in our lab so far. So I can maybe ask you to find the molal, or even just a part of the molal term, like a volume or mass of solvent, right? Kilogram solvent, or a mole of our solute. I could ask you to solve for the freezing constant of a particular solution, or I could even ask you to find the freezing point of a pure solvent or the freezing point of a solution. So it's a question of manipulating this direct proportionality. Okay, in our next video, we are going to go over this concept of our last colligative property, which is called osmotic pressure raising. So osmotic pressure itself is not the colligative property, but in order to understand how osmotic pressure would change when a solute is added, then we need to know what osmotic pressure is in the first place. So next concept, last colligative property is that of osmotic pressure raising, which we'll see in our next video.